Yeah, so I'm Connor. I'm from the Advanced Research Computing Centre at UCL. Yep, we'll talk about unit testing Fortran. Okay, so a little bit about the source material that I'm going to use here. So it's going to be a bit of a live demo, and I've been developing a sort of software carpentry style lesson for unit testing in Fortran. It's very early stages, so there's likely to be mistakes if you do look at it. But that's great for feedback that I'd like. And I'm hoping to deliver this at some point in sort of workshops and actual larger sessions. But we'll be using a repository of exercises that I've also developed to go alongside these lessons. So you get some actual practical usage, and there'll be one in particular we'll be looking at today. So just a little bit of background to make things a bit clearer. What I mean by a unit test, this is unit testing in Fortran, so just clarify that. So what I mean by that is a way of verifying the validity of a code base by testing its smallest individual components or units, hence the name. And units are sort of these three things, these unit tests, sorry, I believe should be isolated, and so they shouldn't rely on any other part of your code base or any strong third-party library in other languages other than Fortran. You may have calls to some sort of API server. You wouldn't want that being relied on in your unit test, and you can find things like that in Fortran codes as well, which should be kind of removed from your testing. You also want them to be minimal, so which is similar to the isolated point, but you don't want to be, for example, testing multiple units in a single test. You should be splitting these up and to the lowest point you can, so that you're only having one unit of code. To make things easier, in the event of a failure, you can find out the problem a lot quicker. And the last point is that they should be fast. So we're on the scale of milliseconds or seconds, because we want fast feedback loops, and unit tests, they help us find bugs and things as early as possible, and that's really their benefit. Okay. So some of the things I try and cover in the lesson I'm developing is a bit of a background on this stuff. And one of those things I think is why do we not already have a lot of unit tests in Fortran? And if you just want to say that the point I'm making here is not because of the language Fortran. It's usually just things that I've noticed in code bases that use Fortran. So the first one I've got that you often see a lot of global variables being used. I've got an example here in this code that I've got on the screen. Don't really worry about what it's doing. Just the point I'm trying to make is that we've got things such as current board, this variable, new board. We've got num rows, num calls. We don't know what these are. These are global variables. In the code base that this is taken from, this code works, but that is a problem. So something better would be this, hope it's large enough, where we're actually passing things into this subroutine. We're passing the board in. We now get information on like types. We know that two-dimensional arrays. We even know things like current board is the input and the output is the new board. We know that that's what should be getting updated. And it allows us to also control the input and output of these units within our test because we can pass those things in. I can't really demo a large multi-purpose procedure in a slide, but that's also an issue, I think. And yet, just the further we move away from this, the easier it will be to unit test Fortran. So the point is that these kind of philosophies are implemented in my exercises, so we won't be showing how to remove those. Yeah. Okay. So what test frameworks? I've sort of said what test frameworks are there. These are actually just the ones I've really looked at. There are more. So there's three here: PF Unit, Test Drive, and Veggies, or sometimes known as vegetables as well. I don't maintain these really. I just use them and sort of learn about them in writing this lesson. So I cover these three in the lesson. Today, though, the thing that's important to me is the supporting MPI. Oh yeah, so this grid I've got here is just a little comparison of things that I believe are supported or not supported on each framework. But the key one is MPI. So what I mean is I'm able to write a single test and then have that run automatically across a range of MPI ranks. And the only one that I can seem to find that works currently, so at the point of making these slides, is PF Unit. So that's what I'm going to be focusing on today, what I'm going to be showing. Okay, so on to the next section, writing a serial unit test. So something that I want to point out is that with whichever framework we choose, we have sort of a shared pattern that we can follow when writing a test. And this kind of applies to any of them. That's why I've got the ability to, importing one of the libraries that we want to use. There's F unit, PF unit here. That's just because there's a serial and a parallel library for PF unit. So we have a module, which would be has a descriptive name, so something would be replaced by the name of your subroutine or function. And then we would define some types, and the key one being that it to act as a parameter. So I mentioned parameterizing a test with MPI, and that's having a single test function running over a range of input parameters. So that's just mentioning the number of MPI ranks at the minute, but these subroutines and functions have inputs and outputs, and we can wrap those up in parameter types, and that makes it a bit easier to pass these things around within our test and just make it clear what we're trying to test and what should be set when we are defining a test suite. Before moving on to that, I'll just mention that PF unit is an additional type, which we'll see, and that's the test case. And that's just telling PF unit what kind of test we're running, but we'll see that in a moment. So yes, so the test suite, this will be something that defines the collection of your parameter sets. So if you want to test some edge cases, for example, you've got some numerical code which you're passing in some row values, negatives, large numbers, you could define different tests in different parameter sets. So you would define that with a test suite. You would then have a section which is your test execution code. So that's going to call your actual source, subroutine, or function, and then make any assertions or check any values on the outputs. And the last bit, you would just have some constructors, which is sort of boilerplate, but can be a bit useful to make things simpler as well. But those are constructors for these custom types that we defined at the top. So yes, notice that this is using types within Fortran, so it is a bit more of a modern-ish feature, not that modern. Yeah. Okay. So now we'll try and look at it live demo. So this is using that exercise of the repository, so it's just a reminder to me, but split into episodes to match the lesson. We're looking at episode 3. So I've got Visual Studio Code open here on episode 3. This is the readme for it. Okay, now just to help me, I have a bit of a script here to keep on plan. So yes, the demo we're going to be looking at has an implementation of Conway's Game of Life, which you may or may not know. But the important thing to know about the program is that it reads in a data file, which is like an initial starting state. Then the system has evolved over time. Sometimes there's some printing to the screen, and then you can reach a steady state. I have some instructions for building in this exercise here. I have already built just to save time, but something important to note is that the way we point at CMake, in case in this scenario, which is the build system we're using, the way we point that to PF unit is by passing the installed library path to CMake prefix path. And that just allows things to pick up. So this is a pre-built PF unit library. So as I said, I've already built, so I'm just going to run the program just to show what the game of life is. So this is just a command. I'm calling the executable game of life from my build directory, and I'm passing in a data file, which I'll show in a moment, but we should see what happens, just so a bit of clarity. So it's just a grid, and it evolves over time, eventually reaches a steady state for some number of generations, or some number of iterations. Just a bit of clarity, show that input file. It's essentially just a 2D grid of ones and zeros. But just so we have the context. Oh, I now can't see. Okay. So the task we're going to be focusing on is with PF unit, and it's going to be this task number 2, which is to write a completely new PF unit test for the subroutine find steady state. So that is a subroutine that exists within this code base. So it'll be helpful to look at that code, but before we do that, I know that my task is to create a test of this subroutine. So I'm just going to go ahead and make a new test file. So I've got the structure here, test, and then as I'm also doing test drive and veggies, it's another directory PF unit, but I'm just going to create a test file in here. I'm going to give it a useful name. So test find steady state. Now notice that the file extension is .pf, and that's a PF unit specific thing. And that's because the way PF unit works, in at least the scenario, the way I'm using it, is there is a preprocessor that will take .pf files and convert them into a Fortran compilable state, so a .f90 file, or well, it's .f90 usually. I'm not sure if it's set up for other versions. But that is why we've got .pf, and this is used just to make things a bit easier. There's less boilerplate that needs to be written in these .pf files. Okay, so I've created this file, and actually I can paste in that skeleton that I mentioned earlier that is shared between the all the frameworks that I've mentioned. So we've got the types that we're going to fill in these sections within this demo and see the final test. But the difference is I'm now importing the source standard test. I'm importing the serial funit library. Okay, so the first thing we want to do is define these types, this test parameter that we want to use, and this test case. To do that, I'm going to look at the actual function that we want to test. So if I go to the source code, I know that it's defined here, and that is find steady state. And we can look at the signature of this subroutine to understand what these inputs and outputs should be. So we've got two inputs, animate, which is likely something to do with animating to the terminal. That's probably going to be what turned off the whole time, because in the test, you don't want too many logs coming to your screen. So that's something that we won't necessarily need to parameterize, it'll just be false by default. Then the actual key important input is input mode, because this is going to determine the starting state and then hence the final state of the system, so our outputs. So that's important. And then we have two outputs, steady state, which is logical, and generation number, which is an integer. So that's the things that we also saw printed to the screen, which is we'll find out if the system has reached steady state and in what generation. Okay, so now that we know these inputs and outputs, we can go and define our actual type. So we can fill in this section. Now I'm going to swap back to my slides just so I can do this at a reasonable pace, that I can get it finished. So we've got that skeleton that I pasted, and I will look at how we define these types. So if you're not familiar with types in Fortran, this is sort of generic syntax. You've got a keyword type, and you can extend base types. And then I've named my type here find steady state test params, just to give an indication of what this is for. So we're extending a type here. This is a base type that is provided by the funit library, abstract test parameter is what it's called, and this allows funit to understand that this is a type and a parameter type and know how to handle it. So that's very important to do. We then define the inputs that we've just seen from the signature. So this is going to be the input board, exact same type as the subroutine of testing. Then we have our outputs. In this case, I'll call them expected outputs, because this is what if I set the value of input board, I in theory know what the expected output should be. Define those in the test parameter type as well. And then the last bit is sort of a bit of boilerplate, but it's something which allows funit to log information about this particular test case in the event of a failure. And we'll see a bit more information about that in a moment. That's just description, and then a type-bound procedure called toString with a bit of a longer name as well. Okay. So the last thing, very important, which is we tag this type within macro. So this is to use that pre-processing. So this will allow conversion from the .pf file to the .f90 file. So that's important as well. We then have an additional type that I mentioned, which is the test case, and we define that like this. Again, we're going to extend a funit base type, which is parameterized test case. So this is going to allow us to be able to do that parameterization that I previously mentioned on our test and just make sure that funit knows what kind of test we're running. And then that's going to have just one value inside of it, which is of the type of the parameter type that we literally just defined. So that's as complex as that getting in a way. And then just like our parameter type, we need another macro. This macro is test case, and there's a little bit more information required than the previous test parameter macro. So first of all, we provide a function, which is get test suite, which will return the test parameters. Well, so this is going to be the thing that defines our test suite or our parameter set, however you want to word it. And we'll define that next. And then the last thing is a constructor for this test case, which basically just converts parameter type to test case type. And we'll see both of these implemented. But now I can swap back to this code, and I can paste this in. So we can see it forming. Just fix the indentation. So we've got our types in place now. Okay. So the next thing is to define the test suite. So I'm going to go back to the slides just to show this, and we can do that. So this is going to be a function, as I mentioned. This is going to return an array of test parameter type, such that we can define sets of different parameters. So we want to build up our input that we're going to pass in. In this case, I'm just doing one scenario, which is because it can get a bit cumbersome to define multiple when it's large arrays like this. But I'm just defining a single input scenario, which is matching the one that I showed through the CLI earlier, which is that model one from that file. This is the same setup. It's actually called an exploder or something, I think, in the game of life, just due to the way it looks when it evolves. So that's what I'm defining there. And then we can define the rest of the parameters. So the way I'm doing that is I'm doing something somewhat confusing by calling the same name as my parameter test type. And this is a default constructor that will be generated when we compile, and the inputs to this constructor for that type just go in the order in which I define them in the test parameter custom type. So we've got the input board, then we have the value that we expect for steady state, which we know should be true, and we know that should be 17 because that was the number of generations it took for this exploder board to reach steady state. And then I've got a description just for what this test case is. Okay, I can then go back to the code and paste this one in place. So we've got that in place there. And we can move on to define where we actually call our source function and run our assertions. Okay, so sorry for all the swapping, we're back to the slides. So let's take a look at how this works. So this will be a subroutine in this case. And just to point out that I can't remember whether it needs to be subroutines and functions all the time. That's why I have these slides, so it shouldn't be too much of a worry that you need to remember these things. But yeah, it's a subroutine in this case, and it takes in one input parameter which matches that custom test case type that we've defined. Again, that's just so funit and pfunit know how to handle this kind of test. Ooh, skip down there. We're then going to call our source function that we're testing, which is find steady state. And if you don't remember the signature, that was the start of animate. So I've said that's going to be default false because I don't want to animate in my test. I'm then going to pass in that input board that I'm extracting from my test suite that I've created from my test case type. And then I pass in some sort of temporary values to get the actual outputs from my call to the subroutine. And these are things that I'm going to compare to my expected outputs, which we can see an example of that here. So that's using another macro provided by funit, funit in this case. So what I'm showing here is assert equal, and this is somewhat of a generic macro, comparison macro, so it's going to do an exact match, so it can't match things like floats and but it does match integers or integer arrays of different numbers of dimensions, and also character arrays, so things like, you might call them strings. But yeah, we pass in the expected value, and then we pass in the actual value, and you can provide some sort of little description or failure message, which will get printed in the event that this assertion fails. Okay, and then we can also do a similar thing to check the expected steady state. However, this is different using a different macro, assert true instead of assert equal. And that's just because assert equal, unfortunately, doesn't support logicals directly, but we can do our own equivalence check and then pass it into assert true. Again, you can add a little description. And you also need another macro at the top there, just to mark this as a test for the preprocessing. Okay, we can swap back and put that in place. I have all these pre-prepared. Fix the location. Okay, and the final thing we have to do is some constructors. These will be the constructors for our types at the top, and also especially this constructor here. So they're converting a parameter to a test case. So again, we'll go back to the slide just to have a look at this. So what this will be is first one is a function, and like I just said, it'll take in a parameter type and convert it to a test case type. And this is going to be very simple. I'm just going to save test parameter to test params. I have tried not including this and hoping magical things happen, but no, you do have to just write this. But that is all we need for there. The next thing is that toString function. So that's converting our parameter type to a string to be printed to the terminal. Again, this is just for a bit of extra logging. And we can see that that's a function which, takes in the parameter type, turns a string or a character array. And the way I'm doing it, you can write whatever you want in here, but I've decided to print the size of the board, input board, and the description. And I'm just saving that to a buffer and then trimming it and saving it to the string to be returned. But this can change how it wants. It's just a bit of logging. You could make it write almost nothing if you're not really bothered about this. But I find it useful to get a bit of information in case of a failure. Okay, so we can then add this last little bit into the test here. Indentation. So now we have our full test in place from the types, test suite, the execution code, and the constructors. So that's the finished serial test. However, now we also need to make sure CMake is aware of this test and will build it and run it. So the way I have this set up is I have a top level CMake list, which is just going to include a subdirectory from that PF unit test directory. And the important stuff is within here, but I'm going to use my slides to explain things. So if I'll just swap back to that to show you what that will be. So first of all, we need to find the PF unit library, which using the inbuilt find package from CMake, and it'll find this from your CMake prefix path, assuming you provided that when you built. We then enable CTest, and we create a library for our source program. I've called it SUT, which stands for System Under Test. Call it whatever you want. And then I'm filtering files for my tests here. So in this case, I've just done one file, so it's probably a bit overkill, but you could include different numbers of tests for a single C test if you want to test, for example, a module, and include all of your tests for the subroutines within there. But the key important bit is this last bit, which is another thing provided by the PF unit library, which is a sort of CMake function. Add PF unit C test. You provide a name, something hopefully a bit useful, describing what you're testing, and then you provide the test files, the .pf files, and then you link to your source library. So we can make sure this is in place within our CMake list, so we can see most of it is in place here. I just need to add this last little bit. Again, I'll paste it so I don't make a mistake. Again, there's other exercises and things within here, so that's why there's some extra tests which need your changes, but we're just looking at one in this case, and we just paste it there. So I'm filtering and defining a C-test. So if I just clear this terminal, we can run our test. So I need to rebuild first. So I'm just going to, I don't need to pass the PF unit library here because that was in the -B section. So this is just a rebuild. But if everything goes to plan, we should see our .pf file converted to a .f90 file. We can see that in this output here. So it's telling us it's test find steady state, PF to test find steady state .f90. And we can see here it's appeared over here. You might be sad, but I'm not going to show it. And I'm just going to run the test. So I'm using CTest here and passing in the build directory and just doing a flag in case there is a failure, and we'll get some extra information because CTest likes to filter out logs. But if I run that, we get everything's passing. PF unit 570 tests. Just to prove that things are actually working, I'm going to intentionally break my test. So instead of expecting 17, I'll expect 16. I will rebuild. Again, it's been regenerated, and I'll rerun the test, and now we get a failure. We can see that it expected 16, but it was actually 17. So I'm confident that my test is actually working as I expect. I'll just fix it and rebuild, and everything should be green again. We get a regenerated file, and the test runs. Okay, so that is writing a serial unit test in this exercise that I've created. Now, I know I'm going quite fast, but I'm going to go on to how we turn this into a parallel unit test. So this is going to use a similar example from the exercises repository. But first of all, I just want to say what do we need from a parallel unit test? Why is this going to be different from the serial unit test? And first of all, we want to be able to run the different numbers of MPI ranks for a single test. So I want to run test, and then I get a range of tests run for, say, 1 rank, 2 ranks, so however many I want. And I want to be also able to assert different things on different ranks. So I may call a function, and I should get different outputs potentially for different ranks. So rank 0 might expect 1, rank 2 might expect 1,000 or whatever. But I need to be able to handle that, and PFUnit does allow that to be done. So we're going to look at another demo. This is same repository, but I'm using episode, I've called them, episode 5 this time. So if I just swap back to here, I'll open the correct ones, episode 5. It's in the challenge directory, not solution. I've got readme here. Okay. So again, this is an implementation of Conway's Game of Life, but this time using MPI. I've already pre-built this. Let me just change the right directory. Okay. Check. Yep. And okay. So I will just run it, but I'll run it with MPI run so we can see. Oh, very helpful. So with 2 ranks, notice there's no animation this time because it was too complicated for me to work out with MPI. But yes, so we've got, I can run with different numbers of ranks up to 8 just for my device. So yeah, it is using MPI. Okay, the task this time is to take that serial test that we've created and turn it into a parallel test. So the serial test is already included in here. There's a few extra comments because this is actually committed to get to this one, but it is the same test, just to point that out. Okay, but what that means I need to do, the first thing is just to import PFUnit instead of FUnit. Okay, so how are our types going to change? Let's go to the slides, take a look. So that's me saying, reminding myself to update it to PFUnit, and now let's look at the types. So actually, there's going to be very little change to this type. In fact, the only change is going to be the type that we extend. So instead of extending abstract test parameter, we're going to extend MPI test parameter. We still get all of the features from abstract test parameter, but this just allows us to use MPI. So everything else is the same. Oh, in fact, I've skipped a step. I need to just show you the signature of the parallel source code, just to prove that I can use the same input and outputs. So we've got for find steady state, the subroutine that we're going to test, we've got the same outputs, steady state and generation number, because it's achieving the same thing. We also still have an input board. It's called global input board this time. That's just because there's some local state within the subroutine. But we do have some extra inputs. We've also got the size of the board. For whatever reason, that is there. It's important to note that you shouldn't really care about the implementation of this test of this source code that you're running. You should just know the inputs and outputs, in my opinion, when you're writing this unit test, because those are the things that you want to be correct, and you should be able to change the implementation while still getting the same answers and still testing the same thing. But a key thing to note is these points at the bottom here, in particular, the base MPI communicator. So it's vital that we pass this in to this subroutine in order for PFUnit to be able to do its testing. And that's because it allows PFUnit to control how many ranks are involved in its communicator. So that's why it's getting passed in here. And we'll see how we get that from PFUnit in a moment. And then we specify also the number of processes, which is just actually specific to this subroutine. It's not necessarily a requirement. Okay, so now that we know the inputs and outputs, we can go back to the slides and we can see that we don't need to change anything other than this base type. That's because we still have an input board. I can get the size of the input board from the input board, so I don't need to specify that in here. I've still got my same expected outputs. I've still got the boilerplate for description, and I've still got the same macro. And the communicator is not handled within here. We'll see how that's handled in a moment. Similarly, for the test case type, there's very little change. The only change, in fact, again, is the type that we extend which is now MPI test case. And that's because this gives these types actually, they give us some base methods, some type-bound methods that we can use, and it allows PFUnit to understand that this is a MPI test case. This is not a parallel serial test case, which we'll again see in more detail in a moment. So again, everything else stays the same macro, just specifying the parameters. So I can make those changes within my parallel test, which is here. This is the parallel test. The only change is MPI test parameter and MPI test case. Okay. So what do we need to change within the test suite? Let's take a look at that. So there is a lot similar with the serial test. We have the same signature for the function. We just still want to return an array of our parameter type. And again, for simplicity, I'm just going to define one board as my input, just so I don't have to, well, just so it fits on the slide, really. But yeah, it's going to be the same explorer type, so I should expect 17 generations, and I shouldn't expect steady state. The key difference is now that we want to specify multiple parameter sets and one for each different input rank that we want to use. And we do that like this. So I'm going to allocate this parameter array with some max number of ranks up to the maximum that I want. It's 8 in this case because that's what my device will work with. And then I'm looping over here and I'm creating these parameters types here. And notice that the constructor is slightly different now. Oh, excuse me. So I've got I'm still passing in the board, the steady state, the generation number, and the description, but there is an additional input at the start, which is unhelpfully named, but is actually the number of ranks for this test. And this is something that is provided by that type that we extended, the MPI test parameter. We can pass in this number of ranks within this constructor. Okay, so we can make that change within our code. So I'm going to give you a copy. I just need to get from the serial. Sorry, the parameter. No, not 1, 2, which is the test suite. Apologies, we're going to lose some comments. But I'll just do that there. But you can see I'm doing what I've just downloaded in these slides. Okay, so what else needs to change? Well, I'm just going to briefly move down to the constructors just to show that actually nothing needs to change here. Test parameter and params for these types is not changed. This remains the same. And the toString function, again, we still have input board, we still have description, there's no change. That can just remain the same. The only change left is going to be within this test suite. And this is actually just going to be a change to this call to find steady state because we are calling a new subroutine. So we can go back to the slides just for a bit of extra information. So there's no change there. We're still asserting the same things. We still have the same outputs. And we still have the same macros and everything. It's just the call to find steady state that's going to change. And this is where we get the interesting bit about this MPI communicator. So that type that we've extended for the test case provides a type-bound procedure, I believe is the technical term, but like a method on the custom type, which will give us an MPI communicator defined by PFUnit. And we can also get the number of processes that we've requested for this test, which will match that input to the constructor we just did. So we can call this here, well, when we're calling find steady state. So I'll again place that into my test. Again, I'll lose comments. Apologies for that. But yeah, the same thing here. Oh, and notice that I'm extracting the size of the board from the board itself in this case. Clearly, I haven't implemented my steady state very well, but yes, that's what I'm doing here. So that is, again, a finished test. The next thing to do is just make sure CMake handles it correctly. So again, I believe I swapped the slides for this. Yes, okay. So showing how things are changing here. This sort of preamble, no change. Still finding the package, enabling testing and setting up all the files and libraries. It's just a very small change, which I'll admit is not well documented. Excuse me. It's not well documented for PF unit, but you just can get it to work at least with this additional line at the bottom. So what this is doing, this max PES, is telling CMake the maximum number of ranks that this test can be run with. So if you specify 9, it will attempt to run a test with 9 ranks. So if you haven't set your test up for that, it will fail. So this needs to link with how you've written your test. So I'll show that now when I add it. If well, when I define this test suite, you notice I've got maximum ranks 8. So this needs to be linked up with that CMake value. But I can add that within the CMake list. So handily, I've got the serial version just commented out there. So I just uncomment it and add max PES 8. And I can rebuild. So clear. Just like a serial version, I will build. Yep. And we can see again the file's been generated, Ignite file, and I can run ctest. Notice I don't need to run with MPI run or anything like that here. Ctest handles it. And in this case, there's many different tests. Again, this is because there's more to these exercises than what I'm showing, but we can see our test at the bottom here, which is PF unit, find steady state tests. I'll do the same thing I did for serial, and I'll intentionally break it just to prove things are working. So I build, file will be regenerated, and I'll rerun the tests. And notice we get some failures now. Okay. In this case, we've got 8 failures, which is actually good because we should have 8 tests, 1 for each input rank, but the sort of everything is the same, so things should fail. You also get a log from each rank that ran. So this is a very long error message because you get 1 log, 2 log for each test. But that means you can, do some good debugging if you get some failures. If, for example, only rank 0 failed, you would know that in your test. So if I go fix the test again, and rebuild, things should pass again. Yes. Okay. So that is writing a parallel version of your test. So I just wanted, in the last few moments, to talk about some tips that I think I've seen from writing testable parallel code. The first one being that you don't need all of your tests to be parallel. So if you're testing a function or a subroutine which doesn't call the MPI library, you don't need to use PF unit, you can use F unit because you'll control those inputs. You don't need to pass in the base MPI communicator, for example. And following on from that, try to do that. So if a subroutine or function doesn't need to call the MPI library, try and isolate that out. So have a function dedicated to, for example, exchanging a halo. Don't do that within something which you could make serial. And then, as I've said, the last one, you need to pass in the MPI communicator for these things to be testable with PF unit, just because it allows us to set the communicator and the number of ranks. Okay. And yeah, that's the end of that.
And so how's the IIDE integration for various frameworks? Can you run and debug individual tests in VS Code?
I have tried to debug Fortran just in general on VS Code, and I've struggled. I usually get to a point where I have it'll hit a breakpoint, and I have sort of addresses listed in my variables. Is this the one?
I think so.
Yeah, okay. In my variables, sorry, in the debug section on the left, but it doesn't link to any variable, so I've not been able to get that working. So if someone does know how to debug Fortran, I can't see why it wouldn't work, because it does, the preprocessor runs and just generates Fortran, so it should be debuggable. But yeah, I don't have the experience for that, unfortunately.
Are you considering putting your costs in the carpentries incubator?
Yes, definitely. As I've said, there's still issues with it. I'll be honest, I started writing it at the point that I wrote the abstract for this, so it didn't exist at that point. So I was thinking, how would be a good way to do this? Started creating it, so I've learned everything as I've done it. So focusing on this walkthrough, there's definitely more updates to this than there are to the lessons, so there will be things to change. So in the future, yes, definitely, I would love to do that. I'd love to deliver the workshop and have other people able to do it as well. We'll listen.
Where does the convention system and tests come from?
Sorry,
yeah, I've seen it once before in another language. Is it some kind of convention?
I'll be honest, I copied the example, I think, from the PF unit documentation, and they used SUT, so I just left it in there. Again, I think I had seen it somewhere else as well, just like this person said, so it seemed to make sense to leave it in there. What sort of comparison to other tools?
Does PF unit support any kind of mocking?
Not easily. To be honest, I would say no, purely for the fact that I don't think it's documented, and so I have no guarantee if it actually works. So there's actually many things implemented in PF Unit partially and seem to have been left over. It definitely needs some help in its development, which is something I'm going to try and do in the future. I've started trying to write some better documentation for PF Unit, and if anyone else wants to help with that as well, I'm sure these things could be implemented, but yeah, not yet.
Can this only run tests in parallel using MPI, or is it a way to test code which makes use of MPI?
Oh, it is a way to test code which makes use of MPI. So I guess, yeah. So it's a bad example for showing one of the points that I mentioned that you want from testing parallel code. You want to be able to assert different things on different ranks, which is then when you get definitely being able to test code that uses MPI. But that is possible, and in some of the exercises I believe I do things like that, because I have a subroutine which exchanges halos, and obviously those halos are different on the different ranks, and I verify that within the test. So yeah, it definitely is for testing MPI code. Yeah.
Have you delivered this lesson in a more relaxed workshop, like, for example, HPC carpentry?
Yes, not yes. Again, refer to the previous point, but yeah, hopefully.